Technical information. My name is Pedro dal Castel. I am a PhD student in Indiana University, Bloomington, and I will be the lecturer in this module, Module 1.2, Introduction to the Cellular Potts Model. So now things will get fun. During the lecture, if you have questions, concerns, suggestions, post them in the Zoom chat. The TAs, the moderators, will answer or defer the question to me depending on the subject. Remember that the workshop is being live streamed, recorded, and distributed. And again, thanks to our supporting institutions, CompuCell3D, which is us, Glimprint Biocomplexity Institute, Indiana University, Bloomington, OpenVT, NIH, and NSF. So I think that's all. So again, the content of this lecture is the Cellular Potts model, the algorithm, how it works, because this will be fundamental to understand how all the plugins, all the behaviors, and interactions play out in the simulation. Otherwise, we're clueless of why things are behaving the way they are. So that's why this is essential to developing simulations in CompuCell. This is our course outline. Again, day one. And hopefully, if everything goes smoothly, we understand where CompuCell, where Cellular Potts model fits among other representation methods, specifically for modeling cellular systems like tissues. The basics of how the Cellular Potts model works, the volume constraint, the quadratic energy constraint, which is what we use for the volume constraint, contact energy, and how to control cell size and shape with volume constraint and contact energy. Okay, so let's start. Since we are simulating cells in a computer, we have to represent them somehow. And there are many ways you can represent cells in a computer. So for example, cellular automata, which is a competing method, let's say, in cellular automata, cells are represented by single pixels. So each cell is one pixel. Okay? Molecular dynamics, which was initially used for modeling molecules and atoms, gases, and fluids, extended for biosystems modeling. They consider the cells as point particles, like atoms, which is very cheap. But you can argue that it's not very realistic. Again, none of them are really realistic anyways. The vertex model represents cells as polygons. And finally, oh yeah, so these are all the ones I talked about. We have molecular dynamics, cellular automata, and vertex model. And finally, Cellular Potts model, which represents cells as a collection of pixels. So here, one single pixel is part of a cell. It's not the cell itself. I think this is all simple by now. The problem now is how cells move, because we represented the cells, they are situated in space, but they can change position. This is essential, especially for developmental simulations where cells move around, they grow, they divide, they interact, all this kind of stuff. Starting with the cellular automata, this is how the cells move in cellular automata. They basically displace. So you delete one pixel and create the pixel in another position. So for example, this cell here, which is this pixel, would pick a neighbor pixel and then delete itself and recreate itself on the other pixel. In the case of molecular dynamics, here they use classical mechanics, which is Newtonian and Langevin integration. You don't need to know why it is the way it is. Like, this is not the topic of the lecture. This is just showing how it works on other frameworks. So here the cells are subjected to potential energies, and they so the gradient of these potential energies are the forces that act over the cell center of mass, and then the cells move as a response to these forces. The force acts over the center of mass, and the entire cell, which is just a particle, moves at once. And the cool thing of a vertex model, which it is similar, the dynamics is similar to the molecular dynamics models. So it is still classical mechanics, but here the forces act over the vertices of the polygon. So instead of moving the cell as a whole, in the previous case, the forces acting over the center of mass, now with the forces acting over the vertices, instead of just moving the cell all at once, the cells stretch and pull, and they move as a consequence of these stretch and pull dynamics. And finally, CompuCell3D with Cellular Potts Model. How does this work? And this is the weirdest of all. That's why I have one tiny bit of history about the Cellular Potts Model. It all started with the EASY model, which was developed by Ising, who would have guessed. This was developed for modeling ferromagnetism. That's why it's a lattice, because the solid, the magnet, is actually a lattice. So the atoms are very well organized. And these atoms can have two states, spin up or spin down. Okay, spin up or spin down. And they interact with neighbor atoms. So they can be spin up up or spin down down or spin up down. And then these atoms, they can change their state randomly, but preferentially to minimize a global energy function. And this is a legacy that we take from the EASY model up to today. We have an energy function where that controls how these pixels change states, and the goal here is to minimize this global energy. Okay? Then, so this is 1924. There was no computation yet. In 1951, this guy named Potts, he developed the EASY model further to allow these pixels to have more than just two states. And what does this do? Well, now you can model, for example, infection spread. So imagine that each pixel represents a house, and the house can be susceptible, can be infected and removed. Removed meaning resistant or dead, or you can even do a four-state system where you distinguish between dead and resistance, and then you have susceptible, infected, resistant, and dead. So this increases the scope of modeling capabilities of the previous EASY model, which was focused on the two-state system of a ferromagnet. And 1992, but created by James Glazier, which is here with us today, and François Granet, what they did is that they extended the Potts model to such that the basic agent, in this case a cell, is represented by a collection of pixels. So in the previous Potts model and EASY model, each pixel is one agent. Now you have a collection of pixels, and that represents an agent. What does this allows is proper modeling of granular matter, such as cells and bubbles. So you can also apply CompuCell3D for modeling bubbles, foams, for example. But the main interest here is biology, and this is what CompuCell was mainly developed for in the end. Again, because of the legacy of this global energy function that we're trying to minimize, we write our constraints. For example, we set volume to the cells by writing energy constraints. And this is what I'm going to explain next. Starting with the concept of energy minimization via gradient descent. In this GIF, this is the simplest possible example of energy minimization via gradient descent. You have balls rolling downhill. That's it. That's the example. What is the energy? It's the potential gravitational energy. And what moves the balls downhill is the force that comes from this potential energy. And then they roll until the potential energy is minimum. It may not be the global minimum. So for example, they might stop in this minimum here on the right side, which is not the global minimum, but it is a minimum. So if they find themselves in a minimum, they stop moving. This is gradient descent. But that we use in the lattice. So let's change the example a bit. And I will give you questions which you will think through and answer in the chat. So here we have a game, simple game. Bob is our character. He is located in this pixel with an energy of value 15. So the value of the pixel where Bob is at is the energy that Bob has. All good? Now, Bob will randomly pick a neighbor pixel and ask himself, is my energy going to decrease if I jump to this neighbor pixel? If the answer is yes, Bob will step to this other pixel. If the answer is no, Bob will stay on the pixel he is at right now. And Bob repeats this process over and over until Bob finds himself in the minimum, in a minimum. Is that clear? So given this set of rules, I have two questions for you. What will be Bob's resulting position? Where will Bob end up at? The other question is, can Bob reach the global minimum? I have colors here to help you finding the what is higher and lower. So 20 is a high energy. Then we have the -10, -5, which are the lowest. -10 obviously being the lowest of all. And we have other local minimas, for example, this 8, this 7. Okay, I will give you 1 or 2 minutes and you will think through it and give me answers in the chat. So someone called Yash Kumar said 8. Suramya asking, can Bob move to the same energy state? Uh, yes. Okay. These people that are answering 8, I will give you 1 more minute to think about your answer, and I will be right back because I need more water. So give me a quick 1 minute break while I will think through it. The ones that got the correct answer, I have an extra question to you. How can you change the rule set such that Bob can arrive at the minimum, the global minimum pixel? So 8 is wrong, 7 is wrong. I mean, they're not wrong, they're possible. 8 is possible, 7 is possible. We can change the starting position Bob is at to get to the global minimum energy pixel. So if we allow Bob to occasionally move to squares that slightly increase the energy, Bob might go to the -10. Could Bob choose 8 before 10 and thus get stuck at 8? Yes, that's possible. Ava, that's possible. Mark, depending on the initial exchange, can get stuck into 8 or reach the 7 below. Perfect. Both are possible. If we change rule 3 so that there is a 50% chance of swap if higher energy, then we could reach the global minimum. Yes, correct. That's it. It depends on the neighborhood you select, right? Yes. Here we are just doing up, down, left, and right. Can he move diagonally? Not in this example. But you can convince Bob to do so. Can he move through pixels with the same energy? Yes. Increase the radius Bob is considering. Okay, good. Good. Another strategy. We are not using this strategy right now, but that's clever. How to get out of pixel with 8 considering the rules defined on the screen? You don't. Why not 7 if he moves down? Could be. Okay, so everyone got a good understanding of the problem, and I think we're ready to move on. So as Troy suggested, and then Suramya also pointed to, more or less, if we let Bob accept increasing its energy with some probability, then there is a chance that Bob reaches the minus 10. However, there is also the possibility that Bob gets out of the minus 10 position. There is a way we can control how much Bob tolerates increasing its energy, and it's via a tolerance energy function. So these function, we set how Bob will accept increasing its energy. Here I'm using tolerance, these T parameter. I'm calling it tolerance. It's how much Bob tolerates increasing its energy. And but again, this function also depends on the energy variation. So the the higher the variation of energy, positive, it has to be a positive energy variation. The higher this variation, the lower the probability that Bob accepts um, increasing its energy. And T, the tolerance parameter, the higher the tolerance parameter, the higher the probability that Bob increased its energy. Okay, so that more or less understood in the Bob's game. Let's move to actual Cellular Potts model. We are prepared. Let's start it. So there are 6 steps. I will read through the steps and we will go through the steps even more carefully. So first step is picking a random lattice pixel. This lattice that I'm showing here in the example on the right, we have medium as green pixels, and we have cell 1 as the yellow pixels. So we pick a random lattice pixel. It could be any of these pixels. And then we pick a random neighbor pixel. Then we attempt to convert neighbor to source. If energy decreases, accept it immediately. And if energy increases, you may accept it. There is a probability that follows. And again, now uh, getting a little bit more technical, it's not a tolerance function, it's a Boltzmann probability function. Questions in the chat? Yeah, okay. First step, pick a random lattice pixel. So I picked a random lattice pixel. It's that one. We call that source. That's our source pixel. Now we pick a random neighbor pixel. Random to the neighbor to the source pixel, okay? It's not your neighbor. It's a neighbor to the source pixel. In this example, I'm randomly picking the pixel on the right side of our source pixel. I hope everything's good by now. So now we attempt to convert neighbor pixel to source pixel. We are asking the neighbor pixel, do you want to become part of cell 1? Yes or no? How do we answer this question? We need an energy, right? We need an energy function. Is the probability of picking neighbor? I will let the moderators answer this one. I will then introduce an energy function so that we can answer this question. Do you want to become part of cell 1? And the energy I am introducing is energy equals the volume of the cell 1. What is volume? Is the number of pixels that belong to cell 1. What is the number of pixels that belong to cell 1? 8. 1, 2, 3, 4, 5, 6, 7, 8. Minus 9 squared. That's my energy. So the volume of the cell minus 9 squared. Given this energy, if I accept that neighbor pixel becomes part of cell 1, joins cell 1, Does the energy increase or decrease? Answers in the chat. Decrease, decrease, increase, increase, decrease. Okay, let's do that. Let's do the calculation here. We have 8 pixels. Okay, we have 8 pixels in our cell currently, which means we have our energy is 8 minus 9 squared. 8 minus 9 is 1 squared. Sorry, 8 minus 9 is minus 1 squared is 1. That's our current energy. If we accept the change, which means now neighbor pixel becomes part of cell 1, now we have a cell of size 9, and what happens? Our energy after the change, so energy after our final energy, so let's say this is our initial energy. Our final energy is 9 minus 9 squared, so that's 0 squared, which is 0. So our energy decreased from 1 to 0. Ekaterina, I'm just giving an example. And I will explain why this example is relevant a bit. So the volume of the cell is the total number of pixels that belong to the cell, Ripla. So 8. Why 9? Because I want it to be 9. I chose this value. I will explain why this form exactly is relevant in a bit. So given this example, our energy is decreasing. Does everybody agree with that? That the energy is decreasing if we make the neighbor pixel part of cell 1? Okay, please type in the chat if you are not following, because this is important. Why this specific form? For now, because I want it. Yes, so here the question is, does the energy decrease if neighbor pixel becomes part of cell 1? Okay, so the answer is yes, energy decreases if neighbor pixel becomes part of cell 1. And what do? We accept the change. So now our cell is 9 pixels big. Okay. Now let's change the example a bit. Let's suppose our volume, our value here is not 9, is an 8. So if I accept neighbor to become part of cell 1, then I have a cell of size 9, which means the energy is increasing, correct? Because I'm coming from 8 minus 8 to 9 minus 8. So in this case, energy will increase, and then we may or may not accept the change based on the probability function, our Boltzmann probability function. So depending on our tolerance parameter, we may or may not accept this change. All right? Okay, I will keep going. This tolerance function, this is a GIF of how this function looks like. In the y-axis, we have our probability of accepting a change that increases energy. And in the x-axis, we have our energy variation. So the larger the energy variation, the lower the probability of accepting the change. But however, when we increase our tolerance parameter, this probability goes down. Sorry, this probability goes up. As we increase the tolerance parameter, the probability of accepting these higher energy increases go up. And why do we use, so let me come back to this example again. So here the system is trying to minimize energy. So the most favorable energy here is the minimum, which means, and where is the minimum at? Is when V cell is equal 9. In this case, the most favorable energy situation is when the volume of the cell is equal to 8. So that's the most favorable situation when the volume of the cell is equal this other number on this function, which means that whatever I set, 8 or 9, this is what the volume that I want the cell to be at. So there is this general way of writing these constraints, which is the quadratic energy. Why quadratic energy? Because it has a minimum. It is well behaved, it has a minimum. And in this minimum, our variable, for example, in the case of volume, our variable V is equal to the V target, the volume target. The volume target is the number you set that controls the volume of the cell. When V equals V target, you are at the minimum. You are at the most favorable configuration. So when you set these kinds of constraints, your variable tends to the target variable. So for volume, you set a target volume, the volume of the cell tends to the target volume. If you set a surface constraint, the surface of the cell tends to the target surface. If you set a length constraint, the length of the cell tends to the target length. This is what the quadratic energy is doing. You are giving a minimum of energy when your variable is equal to your parameter. And we have a multiplier, this lambda, that multiplies the quadratic term. And this lambda, this parameter, is setting the strength of the constraint. So the stronger the constraint, the more close to the target your variable will be. In other words, um, the fluctuation of your variable around the target is lower the higher you set your lambda parameter. In the case of volume, we interpret the lambda volume as the inverse of compressibility. So as you increase the lambda volume, the cells are less compressible, they fluctuate less. And as you decrease the lambda volume, your cells are more compressible, which means they fluctuate more. I like to think that you increase lambda, the cells are harder. They are more like stiff and move less. Is length the diameter? Yes. Mm-mm-mm. No, it's the I don't know in English, it's a semi-axis. Like if you imagine the cell as an ellipse, then you have the bigger semi-axis, that's the length. The major axis, yes. If they fluctuate less, will they be able to reach the target volume? Yeah. They fluctuate less around the target. Any questions here before we proceed to the contact energy? Okay. And what happens if I set lambda to 0? Troy says that the cell vanishes. Okay. Kea? No constraint at all. It's as if we are not setting a constraint, correct? No volume constraint. No energy penalty. Yeah, correct. That's it. No constraint. Perfect. What happens if we set target volume of 0? Cell vanishes, correct? Increase the volume. If I set target volume to 0, shrinks. Yes. Converge to 0. Perfect. Yeah. They will shrink to 0. Correct. Okay, so I think we have a good general understanding of the volume of the quadratic constraint. So that's very good. Now let's move to the next topic. And I just used 36 minutes. I think I am mostly on time. Now let's think about contact. So this is a very simple example. We have cell 1 and cell 2. Cell 1 as yellow pixels, cell 2 as the green pixels. Now consider that each edge between cell 1 and cell 2 pixels count as a +1 unit of energy. What configuration is the most favorable? The left configuration or the right configuration? If each edge counts as a +1 unit of energy. Right? Left? Yash said left to maximize energy, but aren't we minimizing the energy over all the course of this lecture? Minimizing instead of maximizing? Why is the left favorable? Favorable means less energy. Yes, lesser energy, the better. Right to minimize energy. Less contact, less energy. Perfect. Osman, do you understand it? Mika, Alma, Okay. Yes. Okay. All right. What about the second question? So if each edge between cell 1 and cell 2 counts as a -1 unit of energy, what is the most favorable configuration? Suvani? Ritesh? So it's a -1 unit of energy per edge, which means here we have -1, -1, -1, -1, which is -4 for each pixel. So 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4 is, I think it's 24. So -24. No, it's 32, -32. And in the right one, you never should do math live, by the way. And I just did that. And in the right case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, -12 on the left, on the right. And we are minimizing. We want the lower value. So it's the left. Find total perimeter, then count edges as +1 or -1. Yes, Van, that's it. It's left. Okay. Uh, th th people who said right, do you understand why now? Okay. Congratulations. You just understood this equation here. You have a intuitive understanding of this equation. It's usually what shows when you search Cellular Potts Model in Google, and then you go to Wikipedia and you see this. This is what this is telling. It's counting all the edges, and it's counting all the differences between volume and volume target. And then you sum everything into a total energy function, and then you minimize that. And then your entire system changes as to keep cells at certain sizes, keep contacts as cell-cell affinity is set. This is what this energy function represents. But we are here to make things less intuitive. So let's dive deep. Starting with the contact energy. So there is no possible way I can dive deeper on this. So that's why the volume constraint seems very easy. The contact energy is a little bit more sophisticated. Okay. So contact energy we set by pairs of cell types. So suppose we have cell type A, cell type B, and cell type C. We have all the combinations A with A with B, B with C, B with B, and C with C. That's why it's a matrix. Of course, the contact between A and B is the same as with B and A, right? So it's a diagonal matrix. But it's a matrix. All the combinations pairwise between the cell types you specify. Each of the pairs has an associated contact energy. That's why it's a matrix. And then the higher the contact energy, the lower the affinity between the corresponding cell types. So if I have cell type A and cell type B and a high contact energy between them compared to the other contact energies in the system, the lower the affinity between these two cell types because they are trying to minimize energy. So if you set a high energy between two cell types, they tend to separate. And what this ugly function here is, let's break it down. This is basically counting the edges. Basically. It's a little bit more complicated, but it's basically counting all the edges for each pixel. So first, we are scanning all the lattice pixels. This is what the first summation is doing. We're scanning all the lattices of all the pixels of the lattice. Then, for each pixel of the lattice, we scan all the neighbors. So each pixel has a neighborhood that we can specify. We can specify the size of the neighborhood. I will explain that in the next slide. But this second summation is scanning through the pixels that belong to the neighborhood of each pixel in the lattice. And then for each neighbor of these source pixel we are getting, we are asking, are you a pixel of a different cell? Yes or no? This is what this 1 minus delta is doing. Are you a pixel of a different cell? Because if like I cannot consider contact between two pixels of the same cell. It's one cell. The cell has to be cohesive. So I can just calculate contact energy with pixels that belong to other cells. And then I sum the contact energy for each one of these neighbor pixels. So in this case here, imagine that there is a +1 unit of energy per contact. I scan all the pixels of this neighborhood, and then what is the result? It's 1, 2, 3, 4, 5, 6, 7, 8, because there are 8 pixels that belong to a different cell. And the other pixels belong to the same cell, so I'm not taking them into account. If you didn't follow this, it's okay. Okay, all right. I often have to revisit this formula to understand what it does. You don't need to uh, really understand the symbols. You just need to remember one thing. Larger contact energy, lower affinity. Lower contact energy, higher affinity. So large contact energy, cells separate. Low contact energy, cells stick together. All good? I hope so because I don't know if I have a better explanation. Second bullet point saying different cell types tend to separate. If yeah, different cell types tend to separate. Yeah, I don't know if I understand the question. Reply, yes. If they are inside the neighborhood, you account for them. When I say cell, I mean cell, which is a group of pixels, a group of pixels. Luis Jago, if the energy only considers the boundaries, there is no interaction in the interior of the cell. Correct. There is no interaction in the interior of the cell. The inverse relationship you just stated is true to 1 minus delta. Is due to, no, it's due to minimizing energy. The 1 minus delta, this considers when a pixel belongs to the same cell as the source pixel. You are only accounting for pixels that belong to other cells, not the cell itself, not the self cell. That's what the 1 minus delta is doing. So the inverse relationship I stated is due to the J, right? So the delta delta is 1. Sorry. We have delta AB is 1 if A is different than B and 0 otherwise. This is delta. Sorry, it's the other way around. If A equals B, 0 otherwise. But then it's a 1 minus delta, right? So then 1 minus delta, these two invert. 1 if A different than B, and then 0 otherwise. So here we have delta of the cell of the pixel 1, then the cell of the pixel J. J is the neighbor. So this is asking if the cell of pixel A is the same as the cell of pixel J. If they are the same, delta is 1, and then 1 is 1 minus 1 is 0. There is what is membrane frequency, Arian? What is that? Membrane frequency. I don't know what that is. This is not classical mechanics, okay? Okay, good question so far. Now let's understand this neighbor. So this neighbor region we choose the size of the neighbor region. And um, the parameter that controls the size of the neighbor region we call the neighbor order parameter. If you set neighbor order 1, the neighbor region is comprised of the nearest neighbor pixels. So if you take a look here at the image, the nearest of the central pixel are the up, down, left, and right. So this is your neighborhood if your neighbor order parameter is 1. Up, down, left, and right. If your neighbor order is 2, then the neighbor region is comprised of the nearest, which are up, down, left, and right, plus the second nearest, which are the diagonal pixels. So neighbor order 2 is up, down, left, and right diagonals, which are the first nearest and second nearest. If you go to neighbor order 3, you're getting the first nearest, the second nearest, and the third nearest, so on and so forth. And these look different in square lattice, which is the left case, and the right lattice, which is the hexagonal lattice, which is the right case. If you're checking the neighborhood for each pixel of a cell, does that mean that larger cells will generally have lower affinities? Allison, this is a good question, and it depends on the size of the neighborhood. So, for example, if your cell is 1 pixel big, it's like if the size of your cell is 1 pixel, and your neighbor order is, for example, 4, and you grow your cell to a size of 2, now you have one more pixel inside the region, which means you have lower affinity because you added an extra pixel. But this is very, very like going extremely deep into the weeds. So generally the answer is like yes for very small cells. But if your cell is big enough, it doesn't matter. Your neighborhood size will usually be much smaller than your cell size. Okay. All right. So now I have an exercise. And the size here is playing with those two energies, playing with the contact energy and the volume energy. And by playing with those two, I want you to achieve these four first cases. Okay, we have a blob, a normal cell, a blob, an amorphous cell, something that is like less blob, like more weird, more without a shape. Then we have dust, which is like the cell pixels are scattered. And the fourth case where the cell is a single pixel and this cell here doesn't die. It's a single pixel and it's very stable. Single pixel. And I recommend you do not do the advanced challenge unless you are an experienced CompuCell user. So if 1, 2, 3, and 4 are super easy to you, go and do the advanced challenge. If not, 1, 2, 3, and 4. I have the instructions here on the slide. So what you need to do is open to edit and create a new simulation project just as James explained. I will go over with you side by side in a minute, but I want to give you like 5 minutes to go through these steps by yourself. So you open to edit, go create a new project, which is on menu CC3D project drop down, and then new CC3D project. Give it a valid name, select Python plus XML, and then next. Then, if you want, you can change the lattice dimensions to 100 on X and Y. Select periodic boundary conditions for both X and Y. Select rectangular slab, hit next. Then add a cell type with a valid name, like cell, and click add. And next, just ignore the chemical field window. Next, select contact and volume flex, the only two we are going to explore here. And after that, you finish the simulation and then you can start playing with the simulation. To make sure you have only one cell, this is a single cell, okay? It's one cell type and one cell. It's not 2 cells, 4 cells, 10 cells. It's just one cell, one single cell, okay? So it's not one cell type, multiple cells. It's not multiple type, multiple cells. It's not a multiple type, one cell. It's one cell type, one cell. And to make sure you're creating one cell, you go to the uniform initializer in your XML and you change the box dimensions and the width of the cell to match the proper size. So it doesn't matter where you create a cell as long as you have periodic boundary conditions. Properties, you can take a look at the slides here. So I have contact and volume flex. You cannot set periodic boundary conditions for the z axis when your z is 1. You need to put no flux on z. You can only put no flux on x and y. Of course, you can put no periodic boundary conditions on z, but you will need a z greater than 1, which means a 3-dimensional simulation. That's not the purpose here. Keeps crashing when I finish the setup. Check your simulation directory, the name of the directory especially. It cannot contain special characters, it cannot start with a number, and it cannot contain spaces. Contact energy parameters, which are just the J's, the contact energies. I would leave the neighbor order at 4. And the volume constraint parameters, which are the lambda volume and the target volume. Okay, who got the first configuration? If you couldn't follow the instructions, I will go over the instructions here. So if you're falling behind, you can stop for a minute and watch me doing it, because I'll go over step by step, following these instructions here in the slide, and then you can compare to what you got. So here I'll go CC3D project and then new project. So this drop down menu here and then new CC3D project. Click here, opens the wizard. Here in the wizard, you have to give it a proper name. One proper name would be like exercise 1 and a proper directory. So here I have my simulations directory. You can choose another directory. I can, for example, choose my garbage directory, which are simulations I will delete eventually. Python plus XML. So this is, again, this is proper name. If I have a space like this is not adequate. If I have a special character like a hashtag, not adequate. And if I start with a number, not adequate. So very simple names like a word followed by a number. You can use underscores if you prefer. Next. So here I'm suggesting 100, 100. Z is 1. And then just on general simulation properties. And then no flux only on Z. X and Y we do periodic so that the cell doesn't stick to the borders of the lattice. And Z has to be no flux because it's a 1 pixel thick dimension. So Z is no flux, and then X and Y both periodic. Lattice type square, it's okay. Here we don't need to change anything. So just the lattice dimension and then periodic. 100, 100 X and Y, and then periodic X and Y. Next, cell type specification. So the thing I just said about simulation names apply here. So simple names like cell works. Cell 1 works. Cell underscore 1 works. You cannot use spaces. You cannot start with a number. You cannot use special characters. And then you click add or press enter, and then the cell type shows in the table here. And then next. Chemical fields you just ignore. And then here you pick contact and volume flex. All right. Contact and volume flex. And then next. And it's complete. Finish. And then we are left with these. Let me do this again, by the way. So when you finish the simulation, it shows like this. So there is nothing to edit. So what I do is I double click in the project panel on the left. I double click the CC3D file, like so, and then it opens the three simulation files here: the XML, the steppables, and the master Python. Sometimes you close your project panel, and then your to edit is like this. And then what do you do? So if you close your project panel, you come to CC3D project and click show project panel. And then you restore your panel here. Now you can double click and you have your XML and steppables. So in this exercise, what we need is to change the lambda volume and the target volume, which are the volume constraint parameters, and the contact energy parameters, which are these three numbers here, to achieve the four configurations I put on the slide. Okay, so that's the exercise. Who achieved the amorphous and the dust? The 2 and 3. Who did it? Who did 2 and 3? Try did 2 and 3. Boltzmann. Okay. And then the more difficult one, the fourth case. And who is having problems here? Who is having problems? Like couldn't set the simulation. What's the issue, Eva? Explain your issue in the chat. I will help as I can, and we have the TAs, moderators, they will help too. In the meanwhile, I think we can launch the poll for the fourth exercise. I think because it's all right. So you can adjust the parameters in the model editor in Player. So let me run this simulation to show you what I mean. So in the slide here, in Player, there is this model editor panel. You can expand these plugin menus and you can change the parameters directly in Player as the simulation runs. So you don't need to stop the simulation, change parameter, relaunch everything. You can, as the simulation runs, you can change the parameters here, which I am going to do now. So opening Player. Yeah, so here I have the cells running. And as you can see, I have many cells. I want just one cell. To do that, I will go to the XML. Down here, I need to specify just one cell. So I can change the box sizes here to accommodate just one single cell, like that. And now, if I run the simulation again, you can see I have just one cell. And this is the cell. So this is straight up the first case. Now I can come here in the model editor and open these drop-down menus. There is a volume constraint here, and we have the contact constraint. Inside the contact constraint, we have all the combinations here, medium, medium, medium cell, cell, cell. Medium, medium does nothing because there is only one medium cell. Cell, cell doesn't do anything too because we have just one cell. And medium cell is the only one that actually does something. So let's do something very trivial here. I'll increase the target volume to 100. And then the cell increases volume. All right. So if I go to 1000, the cell gets bigger. What happens if I change the lambda volume to 20? You see how the cell fluctuates less here? Let me do 200. Now basically zero fluctuation, right? If I go back to 20, I have some fluctuation. If I go back to 2, more fluctuation. Here I have to be careful that the float values like 2, which has a decimal point, 2.0, if I set 2 and press enter, or like if I do 10 and press enter, nothing changes. You have to do, for example, 10.0. Then you see the change. And what happens if I do like 0.1? The fluctuation will increase even more, right? Let's try to do 0.01. Oh no, my cell is shrinking. I have to be careful. If I decrease the lambda volume too much, the contact energy will win and my cell will vanish because it's trying to minimize contact. So I need like some lambda lambda volume strength here to compensate for the contact energy. Then if I change medium cell energy, let's say if I do 20, see how the cell gets stiffer? Because it's trying to preserve these round shape. And what happens if I change this, if I reduce this to 1, for example? Then I have a more amorphous cell. This is more like the second case. But if I do 0, I have a very amorphous cell, right? Look at this. So this is very amorphous, almost like that dust case. But if I really want to get that dust case, I just set a negative energy and then look what happens. I have like uh no cohesion whatsoever. Like the pixels completely scattered because it's trying to minimize energy and the energy is negative. So the more contact, the better. Uh Eunice, maybe you're not pressing enter. So she's saying here that she's unable to change the parameters on the fly. I set the parameter value and then I press enter. Okay. 1000, enter. See if that solves. If I flip the x, y of z equals 0, z equals 0 with x, y of z equals 1 with the same width. There is not a cell in the simulation. If we flip the x, y of z equals 0, I don't understand that. Hayden, do you understand what Ritesh is saying? If I flip the x, y of z equals 0. Oh, yeah. Yes. So box min is where the cell starts to be drawn, and then box max is where it ends. So box min has to be lower value than box max. Yeah. All right. So could you do the fourth case? Stable 1 pixel cell? What did you have to do? What parameters did you have to use to get a stable 1 pixel cell? Who got fourth case? Okay, I'll do case 4 here for you. Yeah, Martin got it. So you come here, volume, you can even set the cell medium contact to 0, it doesn't matter. And then you increase the lambda volume a lot. So for example, 20,000, I think it's enough. And then you set target volume to 1. There we go, you have 1 pixel cell. Now question, what happens if I do 1.5? Nothing because it's not a float. So I have to go back to the simulation, change my volume to a float, come back here, run again. That's my cell. Lambda volume to a very high level. Value. Now target volume to 1. Okay, I have my 1 pixel cell here. It may still disappear. There is a chance it disappears, but it's very unlikely. What happens if I set this to 1.5? Oh yeah, with contact energy 0. Wow. Why is that? I will leave that for you to think. Let's go to the next exercise. So in the next exercise, now add back a bunch of cells and get them to separate. That's the next exercise. So what you have to do is you come back to your XML and you change the uniform initializer to have more cells. So I could do this, for example, just increase the box size, and then you run the simulation again. Now you have like more cells. If you want even more cells, you can increase this even more. Okay, now we have a multi-cell system. How can we get the cells to scatter, to spread out? What do we need to change? High contact energy between cell 1 and cell 2. Perfect. Yeah. Cell, cell. So notice now that we have more than one cell, the cell-cell contact energy becomes relevant. So if I come here and I set this to like 30, then the cells spread out. So just by setting a high contact energy there. Okay. Now, what can we do to make the cells stick back together once again? I want you to try that on your side and tell me what you find. What happens when you try to revert the change? How do we change so here in the slide, you see the uniform initializer here, where you change to specify like the location where you create the cells, so on. If you just increase the box, like 10 to 60, for example, with a width of 10, you have, in this case, 25 cells. You can increase like 10 to 80, 10 to 80 on X and Y, and that increases the initial number of cells. Kea, my target volume and lambda volume are 50 and 2. Here, to get the cells to separate, you just need to change the cell-cell contact energy. The volume has nothing to do with whether the cells separate or not. Could you get the cells to come back together, yes or no? And did all of them come back together? What happened? Why? Why not all of them? Some didn't. Okay. Small clumps. Why? Why that? Why not all of them? Yeah, they are too far apart already. So let me do that. So I will do like 10, and then they form these small clumps. But here the issue is they have to be close to feel each other, to detect each other's presence and adhere. If they are not close, nothing happens. It's like Velcro, right? Like Velcro has to be like close enough to adhere. If they are far apart, they are not going to adhere, right? So there is an interaction range. Clara said it's like the universe. And if you remember about the Bob example, the Bob issue Bob couldn't see the minimum, right? Here, Bob can't see the -5 pixel. It can only see the 20. So without a probabilistic jump, there is no way Bob can go to the -5. And Clara suggested if we increase the range uh, which Bob can see, then Bob may be able to get to the -5. It's more or less like this. If you increase the range that cells can sense each other, like if you increase the neighbor order parameter, you're increasing the likelihood that these cells will come back together. But you are decreasing locality as it is necessary that the cells come close together, close enough so that they feel each other and connect. Correct. Yeah. Maybe I can do that if I increase like to 50. No, it's too slow. Yeah, okay. Yeah, if I increase too much the neighbor order parameter, it just they disappear because the contact energy becomes overwhelming. Now, one thing that you might have noticed is if I increase the cell energy to 15, the cells don't spread out. But the contact energy between cell is higher than between medium cell. So why are they not spreading apart? Tolerance? No? Yeah. I will jump medium energy. Yeah, you see, cell energy is higher than cell medium energy. Medium energy doesn't do anything. You can do 0, it doesn't matter. You can do 1000. It doesn't do anything because there is only one medium cell. It doesn't do anything. There is no medium in between the cells yet? No, there is no medium between the cells yet. I think this is on the right track. So I will stop the exercise here and provide you with the answer. And then we come back to the exercise so I can help you out with reaching these configurations. So when the cells are in direct contact between each other, you have just one surface, just one border, which is the border between cell 1 and cell 2. So here we have two cells. They are the same type. They are cells of the same type, but they are different cells. So cell 1 and cell 2 in contact with each other. There is only one boundary between these two cells. However, if I put medium in between, now there are two boundaries. Each cell has one border with medium. So we have twice the amount of border when there is medium between the cells. So if you want to get like a neutral contact energy, as if medium A has the same affinity as AA, you have to multiply your you have to multiply your JAA by 2. So if I come back here to this simulation and I put like I specify twice the contact energy. So sorry. So here what I mean is if I set my cell contact energy to twice the medium cell energy, then this is neutral. Then they have no preference between medium and cell, and they will just diffuse. Eventually, they will separate. Hmm. Yeah. Eventually, I mean, it takes time because it is probabilistic. Maybe if I just increase the fluctuation a little bit, that will make the system a little bit faster. But like you can already see some cells. Okay, let me get this back to 2 and increase the temperature. Yeah. So I'm just increasing temperature here. I'm increasing the tolerance so cells are more susceptible to increasing their energy, just so that the system achieves higher energy states more frequently, this basically messes up the system, and then the cells are more likely to move around. You are increasing the diffusion of the cells. And you can see that, I mean, the cells are still together because they started together, but with enough time, with enough simulation time, they will be scattering around, forming clusters here and there, but with no preference. As opposed to anything smaller than 20. If I go 19, yeah, it's a small difference. If I go to 15, now they start forming more cohesive clusters, right? And if I set to something like larger than 20, like 25, then they will decisively separate. And this is why when you put medium in between, you have twice the amount of border. Here we have box min and box max. We have the lattice here, x and y. So if you set box min 20 on the x, this is where the cells will start to be drawn, okay? It will go up to 80. So 80 is our other limit. And then same thing for the y. So there will be a 20, there's a 20 there for the y, and there's an 80 for the y. So this square region here in the middle is where CompuCell will draw the cells. Okay? Now we set a width of 10, which means every 10 pixels we draw a cell, which means there is 30, 40, 60, 70. So we'll have cells like this, so on and so forth, until everything is filled. Is that clear? And how does that tie to the actual volume of the cells? It does not. The initial condition doesn't play a big role in the steady state of the steady state. It does not play a role on the steady state of the cell. No matter the starting volume of the cell, I mean, there are some situations where it matters, but in general, the starting volume of the cell doesn't matter for the steady state volume of the cell. So you can, for example, if you decrease the width to 5, in practice, what happens is that you have double the number of cells, but they will grow back to their shape, to their actual size. So if I do like 20 pixels, let me reduce this. So these are large cells, and what will happen is that they will just shrink back, right? They will shrink back to the size they are supposed to be at, like this. See? They start filling all that space, and then you run, they quickly go to the um, um, relax to the target volume that you specified. Is that clear?